let's talk Bayes' theorem. All right, so Bayes' theorem is the probability of an event based on prior knowledge of conditions that might be related to the event. So basically, this is used for updating previous probabilities using new information, right? That whole prior knowledge piece, so that we can arrive at revised probabilities. So we can change things, say, well, if we now know this, how does that change things? Okay, and the big thing with that is we use like the word given, right? Now we know A given B. So what does that mean for things? All right. Now, this page looks very confusing. That's fine. Just let's focus on, we have three pieces. 1, 2, 3. Okay, so the first one, this is kind of the crunched down, simplified version of Bayes' theorem. It says the probability of A given B equals the probability of B given A times the probability of A divided by the probability of B. Now, number 2 is the same formula. You'll notice the numerators are identical. Probability of B given A times probability of A. It's the denominators that are different. But, as you see in number 3, the probability of B, the denominator in 1, equals the probability in number 2. Now, you might say, well, why would I ever use the second one when it's so much more complicated? And I get that. 100% I get that. But sometimes you don't just have all the information you need, right? Sometimes you have a big table, you might not, or something is given to you. So depending on the information you have, obviously if you can use Formula 1, so much easier. But Formula 2 will also get you the same answer. So let's go ahead and jump into a question. We have ourselves a table. Horizontally, we're talking about glasses. So students who wear glasses, this is a yes or a no, right? Yes across the top, no across the bottom. Then we have 4 colors of t-shirts: green, red, blue, and orange. And then obviously we have the total. So we have 105 total students in the table accordingly. So use Bayes' theorem to find the probability that the randomly selected students wore a red shirt given that they were wearing glasses. Now we're going to use Bayes' theorem for this, so we're going to come back to this, but I'm a big fan of using the letters in my probability statement that I'm given. Okay, so we're saying wore a red shirt, probability of red, so probability of R, given that they were wearing glasses. That's a yes. So we're doing the probability of R given Y. So think about Bayes' theorem. That means we're going to find the probability of Y given R times the probability of R divided by the probability of yes. Right? This is what we're looking at. Okay, let's do that. And to do that, so we know these are the 3 pieces we need. Well, let's find those probabilities independently of each other. So the probability of yes given red. Okay, so given red means I'm going to just look at the red column. So 6 for yes, 21 for no, 27 total. So the probability of yes is 6 out of 27. So that's probability of yes given red. Now let's just find the probability of red. Okay, well, that's out of the total, right? So that's 27 total reds out of 105. And let's find the probability of yes. Well, the total yeses are 14 out of 105. So now we have our probabilities. And I don't know how you feel about doing probability problems, but I prefer to say, okay, this is my formula, these are the pieces I need, and then I like to find them, just like I did here, write them down, then it makes it easier for me to substitute them in correctly. I find correctly, not incorrect. Sometimes I find that if I try to just go straight from the table to the formula, I just make some silly mistakes, and I want to avoid that at all cost. So, okay, so now I need a new page. I want to do this. So let's go ahead and plug this in. I guess I didn't give myself enough prep space here. So we're going to take yes given red times probability of red divided by probability of yes. Now you'll notice in the numerator, the 27s, denominator to numerator, will cancel out. So I'm left with 6 over 105 divided by 14 out of 105. And if you know how to divide fractions, you know that we're taking keep, change, flip, which means my 105s cancel out, and I'm left with 6 over 14, which does reduce to 3/7. So this is the probability that some randomly selected student wore a red shirt given that they were wearing glasses. Okay, now that's basically it. You could be done. But I want to show the other formula. Okay, so knowing that probability of yes given red, we know that. 27 over 105. Probability of red is 6 over 27. And then we have the same thing to start in the denominator. Now we have red complement. Okay, so think this through. If 27 are red, then the rest are not red, right? So that would mean 105 minus 27 is 78. So the probability of yes given the red complement is 78 over 105. And the probability of red complement, well, that means everything that's not red. Well, again, if there are 105, that means there are 78 that are not red. Okay, probability of red complement would give us 8 out of 70. Oh, I think I mixed those up. My bad. I have them written backwards. Probability of red complement, that's this one here. Sorry, I wrote them backwards on my paper. Because there are 105 total. If 27 are red, then 78 are not red. And then for red given these denominators here, 27 and 78, these are the reds, these are the not reds. So given not red, how many are yeses? That'd be the 8. Okay, so sorry about that initial confusion there. So now we are ready to play with this. So we can reduce, right? The 27s go away, so my numerator is 6 over 105. I can reduce in the denominators, and I get 6 over 105 plus 8 over 105, which the denominators are the same, so we just add. So we're going to divide by 14 over 105, and by now you should be going, hey, that's literally the same thing we just did. And you're right, it is. So I multiply by the reciprocal. Those go away. 6 over 14 reduces to 3/7. And that is playing with Bayes' theorem in 2 different ways.